right. Hi, everybody. Thanks for coming out to the Near Web series. I'm Glenn from UBC Blockchain Club here with Oliver and Ryan, and we're here to present session 5, which is about smart contracts on the Near blockchain. So just a brief overview of what we'll be covering today. We're going to start with an introduction to smart contracts and some of their use cases. Then we're going to make some high-level comparisons between the Ethereum blockchain and the Near blockchain and how the contracts operate on both. And then Ollie will walk us through a live contract demo and we put it all together. So, smart contracts, that's why you're all here. I might get into what they are. So, in short, a smart contract is code that is written on the blockchain. And this code basically comprises a contract where the agreements between, or the terms of the agreement between the two parties are formally written into the code and posted on the blockchain for everyone to see. This makes it immutable, public, and has an infinite lifetime. And since this is written in code and not in English, this sort of operates in a binary system where conditions to the contract are either met or they're not met, leaving no room for a subjective interpretation. You can't half meet a condition when there's only a true or false output of the contract. So smart contracts, like many normal computers, are Turing complete, and they can perform many regular functions like a computer can. Traditionally like while loops or if statements. If statements is a common format for a lot of smart contracts to follow. So basically, like you would see in anything from an Excel spreadsheet to any other coding language, there is conditions for the satisfaction of the if statement. If the statement is satisfied, then there's some sort of function or output that is given. And if the statement is not satisfied, then there's some alternative output. So in this theoretical example here, let's say the condition for satisfaction is that to receive the NFT, you need to pay 68 NEAR tokens to the contract. So if a user deposits the 68 NEAR tokens to the contract will automatically transfer the NFT to their account. And if the 68 NEAR tokens are not deposited, then the contract will do nothing. So this is a very simple example, but it provides sort of a holistic outline of the structure that many smart contracts operate on, where there's a set of predetermined inputs that must be present for some sort of output function to be initiated. And these inputs can be directly entered into the contract, like in the previous example, where both users had to upload the funds, the NEAR tokens, and the NFT in order for the contract to execute, or they can be directly entered through a call of the function, directly or indirectly through another smart contract. And also these inputs can be sourced from the real world using something like an API. So real world data can be transmitted through services called oracles into a method that's readable by smart contracts and can be used to basically determine if contract satisfaction conditions are met or not. This real world data can range from anything from asset prices to who won the Lakers game last night to trading volume. It really depends on what the contract is looking for. And once the data is transmitted into a mode that is readable by the contract, it can then be used to determine whether conditions were met or not. So like everything in life, there is an inherent pro and con to smart contracts, just like everything else. So some of the big benefits that smart contracts provide is automation, and which inherently gives lower cost. So since after the contract is written, there's no manual work required, there's no storage, there's no intermediaries to verify the contract, they self-execute once these conditions are met. This, in theory, would give lower cost than, let's say, paying for a legal team or escrow for a house or other traditional services where a middleman takes a cut of the profit. Maybe this might not be the case when gas fees are around 80 bucks on Ethereum. Maybe you might be better off doing something in person, but in theory, the automation provides lower cost. The contracts are very secure as they use the most secure method of encryption, asymmetric encryption available. The contracts and every aspect of the contract is explicitly defined in the code and public to everyone to view, which gives greater accuracy and transparency. Anybody who knows how to read the language and understands a smart contract can read through it and see what's happening before entering anything into it. So, and also there is no execution risk because, yeah. But there also does come with a set of drawbacks. for this as well. So since these are codes written by humans, there is high potential for human error. Smart contracts are particularly sensitive to bugs in code. It's not like a traditional front end or a website where if it works and it looks good, it's okay. There's specific things that hackers do look to exploit in contracts. So basically, there's a lot of work that goes into verifying contracts and making sure they are perfectly operational before they're publicly posted, because once they're posted, they can't be altered. Also, there's a potential for a lack of privacy where maybe two addresses that are publicly known are engaging in a contract. Everybody on the network, since it's distributed to all the nodes in the network, understands that these two people are engaging in some sort of agreement. Another drawback is that this may be difficult to understand for regular people in layman's terms, since it's all written in code and in coding languages that are more complex than other ones. It is hard for people who don't understand, coding in general, let alone blockchain and Solidity development or Rust, to read the contract and know what's actually going on. Whereas like a traditional legal contract, it is all written in whatever language you're reading it in on paper, so anybody can theoretically understand it. And also regulation has not caught up with this technology, so there's potential for innovation to be stifled by regulatory bodies in the future. So that's a brief overview of what a contract is, and now just quickly, what are some of the things they're being used for? So first, I'll start with a couple simple uses of contracts, and by simple, I mean functions and processes that can be done with a single contract. So in the case of an insurance contract, there's some event that triggers an insurance policy, and this policy has been agreed upon by the insurance provider and the insuree beforehand, just like traditional insurance. But the difference between a smart contract insurance and regular insurance is that the contract can automatically execute the payment, let's say, of the insurance policy if the conditions are met. So just to demonstrate this, imagine Farmer John has crops that, they go bad if the temperature has been over 100 degrees for 5 days. And if he wants to buy insurance on his crops to make sure they don't fail, the contract basically says that if you pay some fixed payment, $100 a month, and the temperature is greater than 100 degrees for 5 days, we will reimburse you whatever here it says $10,000. So $10,000 insurance for your crops. And if the temperature is no longer over 100 degrees, then we will not do anything and we'll just continue to collect your payments. So what this does is basically automates the insurance process and uses an oracle to call this data here, the temperature in the whatever region this farm is located on, to automate the process. This can also happen with loans and with escrow. For escrow, for example, like the example given earlier where an NFT and funds were deposited to a contract and distributed. The same thing in theory could be done with a house if the house deed could be tokenized and the house buyer was willing to accept, let's say, USDC for their house. Both of these assets could be deposited to the contract and automatically distributed, which cuts out the middleman, the escrow manager, which normally takes around a 2% fee on a real estate sale, which is quite hefty when you're thinking about $500,000 property. And there also is a lot more complex uses of smart contracts, which basically require a lot of interoperability between different contracts and many different contracts. So decentralized applications have been built basically through a combination of smart contracts, which each one has a specific functionality, and they're intertwined together in a way that allows an entire application or process to be built on the blockchain. So for this example, we'll just briefly go over what Curve Finance does for different users. We're not actually going to go down into how Curve Finance works, but basically just showing that there is quite a high level of interoperability between the contracts that this platform operates on. So as a liquidity provider on this platform, I can deposit my tokens. Say I want to upload DAI to their front end, and I can pick which pool I want it to go into. And then after that, that's sort of all the interaction I do on a user basis. Then the platform then goes, and depending on which pool I selected, they will basically transfer my funds there through a series of contracts. Let's say I pick the compound lending pool, then something happens where this interacts with another contract, which gives me my CDAI, or the compound liquidity provider tokens, in exchange, which I can then go and stake through a different contract. I mean, we don't need to get into the nitty-gritty of how this process actually works, but basically just need to understand that there are a lot of things going on in the background on a platform like this. And to the user, to any of these users around, it might be as simple as inputting funds and receiving some interest back, but on the back end, there's a lot of contracts at work that allow these things to be built. For a trader, same thing. If I want to swap USDC for DAI, all I do is basically go onto the platform, pick out the swap that I want to do, and it will automatically do it through a series of contracts and deposit back to my account. Same thing with lenders. Now, this isn't meant to go over how the platform works, as I mentioned before, but basically just gives you an understanding that there are a lot of different working pieces behind these platforms, and smart contracts are sort of the infrastructure in which all these things are built on. Here's just an example. When I deposited some money to this LP as an LP onto this platform, there was 8 different addresses, there's a couple different burns, and this was without the staking at all. This is just simply depositing the funds. There's a lot more going on behind the scenes than it appears. Anyway, I hope that gives you guys a good overview of what smart contracts are and some of their use cases. Now I'm going to pass it over to Ryan so he can go into comparisons on Ethereum and Near.
Awesome, thank you, Glenn. I can take a screen share from here, so I'll just turn that on. I'm assuming everyone can see that. Wonderful. Okay, yeah. So kind of like Glenn said, it's kind of a good basis to compare building on Ethereum versus building on Near, just because Ethereum has such sort of a big developer community compared to Near. And so it would be quite helpful for us to sort of go over the two and compare them. And so let's kind of just get into it. So let's start by just comparing the two blockchains. So Near is implementing a lot of interesting things that Ethereum has problems with. So because Ethereum is a proof of work blockchain, it sort of has a lot of scalability problems. So some of these are like high gas fees, slow transactions, high failure rate. I mean, to put it into perspective, imagine you were accepting a GitHub pull request and merging it to a branch, and that would cost you like $80 or something like that. That's pretty much how bad the gas fees can be on Ethereum. Now, Near solves this problem because it's using proof of stake and something called sharding. So sharding is basically splitting the network up into a bunch of smaller pieces, of which we're kind of referring to as shards. And this is kind of helping to solve the scalability problem. And a few of the nice things that we get with solving these problems is that, first of all, gas fees are literally 10 to 100 times cheaper than Ethereum. So you're not gonna have to pay like $80 just to do a transaction or put a new smart contract on the blockchain. And also the block time is much faster on Near. I mean, you have a 1 second block time with 3 second finality, while on Ethereum, it's literally like 12 to 14 seconds. So it's 12 to 14 times faster than Ethereum, which is a huge difference, and it is making things a lot easier for developers. In fact, one of the nicest things about this is it really lowers the barrier to entry for new developers coming into the ecosystem, because they don't already need to hold a lot of Near, for example, to start, compared to someone on Ethereum, where you kind of already have to have a good amount of ETH in order to begin sort of immersing yourself in the ecosystem. And so if you just want to cover a few primitive differences that you're going to kind of encounter while you're writing code or building things on each blockchain, right? If we start with the accounts, Ethereum supports 2 types of accounts. So you have contracts as well as externally owned accounts, and each one of these kind of has their own private key that you can use to access validate transactions, et cetera, et cetera. Near supports a singular type account that has unlimited scoped keys. And then when you're storing state, again, this is one of the issues with Ethereum, that state is replicated across every single node on the blockchain, which is gonna take significantly longer than Near, where you're sort of isolating state to one sort of home shard per account, which is much faster because we're using sharding. And then for transactions, Ethereum supports transfers, contract deployments, as well as function call transactions. On Near, you have 8 sort of composable transactions, and you can use these to use sort of a bunch of different methods that Near gives you access to while you're running code. And then of course there's gas. So Ethereum gas price is determined by the network usage. So if you have a lot of people using Ethereum at the same time, you're gonna notice that the gas fees are way higher than when there are a few people. And so, which can be kind of annoying because they're not constant. So if I wanna deploy code or do really anything at peak hours, it's gonna be much more annoying or expensive than if I want to do it, at like 2 in the morning when maybe less people are using it. And now Near's gas is kind of controlled to limited shard congestion of 50%. So we're keeping that gas fee down, making it easier for developers and people using the blockchain. And then for blocks, Ethereum blocks are created using proof of work consensus, although they are planning to switch to proof of stake, which Near is using, although we don't really know the timeline for that. They're doing that at a rate of 1 every 15 seconds. On Near, you have blocks being produced using proof of stake at a rate of 1 block per second, so considerably faster. And then if you want to just compare contracts on Near versus Ethereum real quick, you sort of have different standard names, but they're really doing the same thing. So for example, NEP 141 and ERC20 are both the contract standard for a fungible token, which is literally just like some kind of token, like any coin that you have on the chain is using those standards. NEP 171, ERC 721, it just stands for non-fungible token or an NFT. So a lot of the stuff that you're going to be doing is quite similar, although you're just going to be doing it in a different way. And so, for example, if you look at addresses on Ethereum, it has a native type address, while on Near, since we're using Rust, addresses are of type string, and you need to validate that they're an address through env is valid account ID, which is basically just a validator, because that's not built in natively to Rust, because Rust is not a language that was created specifically for blockchain use, unlike Solidity, which is what we use on Ethereum. And then, of course, Ethereum has mappings versus collections, which we're going to cover later on. And if you want to run a local node on Ethereum, you're going to be using Ganache, while on Near, you're going to be using NearUp, which you can look at in the documentation. So just to cover some mapping differences, we have Rust and assembly script, which is what we're writing our code in. It's going to be compiled in the Wasm virtual machine. And so you sort of have different VMs or computers that the code is running on for each blockchain. So some of the nice things about building on Near or with Rust in general is you have a pretty large existing dev community, because Rust is not purely for blockchain. So it's a lot less niche than something like Solidity. And it's much more general purpose. So again, you're going to have quite a large developer community. If you ever have problems with the language, and you want to go on Stack Overflow or something, there's going to be a very good chance someone else has had that problem. Now, again, at the same time, these can kind of be cons. So obviously, Rust is not originally designed for blockchain development. So you're going to be lacking things like formal verification, and you're going to need to use validators like this env is valid account ID, which you wouldn't have to do on Solidity because you have type address, which is built in natively to the language. And now when we're building on Ethereum, we have our custom language that it's using, which is Solidity, which compiles to the EVM. And one of the nice things about the EVM is that there's actually quite a few blockchains that are EVM compatible. So you can sort of take your Solidity code and run it on multiple different blockchains, which is quite convenient. Some of the pros, again, Solidity is designed for blockchain development. It has formal verification built in. And then the cons, obviously, at the same time, it's a niche language with quite a small developer community, so it's hard to learn, and the barrier to entry is a little bit higher than it is when we're using Rust, just because so few people are using it. So now, let's just run into a quick example. Code example. So I'm kind of going to compare a couple of token standards. We're going to be comparing that for fungible tokens, ERC20 and NEP 141. And then I'm just going to go into a couple of contracts. This is going to be super quick. So over here, we have on the right side, we just have the token standard for an ERC20 token on the Ethereum. On the left, we have the standard for NEP 141, which would be on Near. So by the way, I got these just from Google. Like, I didn't have to write these on myself. If you look at something called eips.ethereum.org, this is going to give you all the token standards for everything on Ethereum. So I'm getting all these functions from there. And then for Near, you can use Nomicon, which gives you all the token standards for things on Near, which is super convenient, makes our lives a lot easier. And so if we just dive into this, we can kind of start by looking at the ERC20 token. Some of the things we can already see is that we have that native type address, which comes built into the language. And address, by the way, is of type. So if we want to just put in a default address, something like 0x0 would be an example. And then you can just add like 1, 2, 3, 4, 5, 6, whatever the address is. So this would be an example of something that's natively just of type address. In Rust, when we're doing that, if you look at the receiver ID here, this would stand for the address of the person receiving a transfer. And so here it's going to be a string. So instead of having it built into 0x0, we have to put that in the string. And then here we just have some functions. So for example, here are some view functions. So you can look at the name, symbol, supply of your token. the balance of at some user. Over here, we have a transfer function. So this is actually going to be a good one to compare to near. So again, here on Ethereum, we have a function transfer. It takes an address to, and then a UNT56, which is just the value. And then here on near, where we're kind of doing the same thing, we have a receiver ID, which is of type string. We have an amount, which is also of type string instead of being an integer. So that's something else to note. And then there's a small memo that comes with it. And so that sort of highlights some of the differences when you're building on the two blockchains. And now if I want to just dive into an actual contract real quick, let's start again on the right side of its Solidity. We have an ERC20 token. So some of the things that we'll notice that we mentioned earlier are mappings here on Solidity. So we're mapping an address to a UNT56 and we're calling this balances. So really all that means is if I were to call balances at like some address, whatever that address would be, it would just return. So you have kind of a key value pair, right? So it's going to return the balance of whatever that address is as a UNT256. And using that, we can basically get the balance of, I mean, any address. So with this, that holds this token. And so we have a couple other things like the total supply, string name and symbol. And so when you first instantiate this contract, you're going to have a constructor where you're just setting a name and symbol. And then we have a couple of different names, just like we looked at in the contract standard, right? If you guys remember looking at some of the view functions, we have name here. This is just going to return name, just view functions. Symbol is going to return symbol. The total supply is going to return the total supply. And then down here, just like we saw that transfer function earlier, here it is popping up again with some real code in it. So we're giving it an address to and an amount. And then, yeah, over here is just sort of the code for that. And if we want to compare this to a Rust contract, again, because Rust is not natively built for blockchain use, you can see up here that we have to import something called the Near SDK in order to actually build on Near. So that's what's sort of going on here at the top. And then if we go down here, we have, this is our resolve and transfer function that we saw earlier with the sender receiver ID and an amount. And then if we go down, we have some receivers and other things. But what I really want to highlight is comparing a function on a Rust contract with a function on a Solidity contract. So let's take a look at this total supply function here. If we go down here, we can see the total supply function on a Solidity contract. And this sort of gives you the difference between the two, right? And so you can see in Solidity, we're using a lot more sort of keywords than we are here on Rust, for example. And then if we go down here, we want to look at the balance of, this is the same thing down here, which is, yeah, so which is a little bit different on Solidity than it is on Near. And so if you guys want this code or want to compare, again, you can just take a look at the EIPS and Nomicon pages and go through those, sort of compare what the difference is, especially if you're coming from an Ethereum background. And from there, that's kind of going to help you get a better understanding. But those are that's sort of a high level overview of the difference between two of the same contracts on Near versus on Solidity. And those are some of the differences when you're going to be building on Near versus Solidity. And so with that, or on Ethereum. So with that, I'm just going to pass it over to Ollie, who's going to go a lot more in depth.
Hey guys, how's it going? Hopefully you can see my screen. Maybe someone just put a message in the chat to confirm you can just see. There's just a PowerPoint slide up right now. Okay, great. Thanks, Katya. So the first thing we're gonna have to do is set up our dev environment. So I've already done this, so I'm not gonna go. I'm not gonna actually write the code out to do this, but I'm running the project on Windows. So in order to do that, in order to like interact with Near through the CLI, which is something we're gonna get into, you need to sort of install this Windows System Linux. So like for non-devs, it might seem like a bit of a hurdle, but it's pretty straightforward to do, and it's pretty detailed documentation on the Near docs. So yeah, check that out. At some point in this, I'll post a link to it, maybe at the end, or maybe Ryan and Glenn can do that while I'm going through it. But the first thing you're going to want to do is install Rust up. This basically allows us to use Rust in our dev. We're going to want to configure our current shell. We do that by running this command. And we're going to want to add a special tool that's going to allow us to basically generate the WASM files that we're going to need to deploy contracts to the blockchain. And that's going to be using this command, Rust up target add WASM32 unknown. I find the notation to this a little interesting. Maybe Dorian could comment on it. It's probably a little outside of scope for like what we need to accomplish here. I thought it was kind of funny how they have this unknown stuff here. You're going to need to create a NEAR account in order to do this demo. I mean, at this point, I think most of the attendees should have that. In session 3, we set up a NEAR account and some free NEAR was given out. So hopefully you didn't miss out on that. You're also going to need to install Node.js. You know, pretty much anyone doing any development in Web3 is going to need to have that installed to be familiar with it. It's an extremely useful tool. And you're going to need to install the NEAR CLI, of course, and that's just going to be running this command here. So given that, you guys don't have to get that all done right now. It's just a little background stuff. I tried to make a joke at the end. It's hammer time. I mean, it's demo time. I don't know, like when you demo, you hammer stuff. Okay, that joke. So let me do a share screen. So right near here, we're gonna have an empty project, and we are gonna start building the demo out. So I'm just gonna post a quick link to the demo that we're gonna be doing. That is gonna be here. It's basically sort of like the first real demo that you would do if you're going through any of the NEAR stuff. And in that same root link here in docs, you should also be able to find stuff to setting up the NEAR CLI. So I've kind of set up all my commands ahead of time, so I'm not actually going to be writing this up from scratch, but we're going to need to set up a project folder. And the first command we're going to do that is this here, cargo new Rust. And we're going to see it created a folder here. So cargo downloads Rust package dependencies, it compiles packages, it makes distributable packages, and it uploads them to crates. And crates is a Rust community package registry. That's something we'll touch on a bit, but it's a little more in-depth Rust stuff. So let's just do a quick command to change our directory to where we just created the project. Okay, now we're in Rust Counter tutorial 3. And let's take a look at the folder structure that was created in the first command here. Okay, so we have this source folder. We have a git ignore, and we have a cargo toml. So the git ignore file, for anyone who's familiar with dev stuff, I mean, they should be familiar with that, but it's kind of interesting. It's like when you first start off, it's like this sort of like mysterious file. But sort of like the paradigm for development is like you need to like sort of create projects and then you upload them to like a shared repository where other members of your team can sort of pull them and access them. And the git ignore is really useful because it allows you to specify all the files in your project that you don't want to upload to that sort of shared repository. And that could be things like, you know, when you install packages, like you're installing sort of like dependencies. So that could be like a lot of node related stuff. There's a lot of files there that would take up a ton of space up online, and they can just be sort of installed by other people after they pull the project. Other things that you wouldn't want to be posted there, and we'll show that sort of at the end of this demo. Like you might have full files called like environment files, and in those files, like you contain things like private keys and things like that that you're using to sort of basically like log in and sign transactions and things like that in the back end. So those are definitely things you don't want to have uploaded to a shared repository. So yeah, just wanted to sort of touch on that. So right now I'm in what's called a bash terminal. So what I'm going to do is I'm going to get rid of this main file. So we tend not to, we don't actually build near smart contracts in Rust using the main file. They use what's called a library file. And library files, they just work well for compiling WebAssembly. So that's sort of the reason for that. So these are just a couple of quick short commands that you can use that bash recognizes in order to, as we saw, delete that file and sort of create this empty file. Now we can take a quick look at the cargo toml file here. So this is sort of like the default file that was generated. I'm going to copy what we want to put in there for this current project, which you can see is in that link that I sent at the beginning. And we'll just take a quick look at it. So as I said before, cargo is the Rust package manager. So you can kind of think of like npm and package.json, for example. TOML stands for random bit of trivia. Tom's obvious minimal language. Maybe someone could sort of post something on that in the background as to where that comes from. I'd be interested to know. And so we see under the package header here, we have some fields. So we have the name of the projects we're going to run. This is pretty important. You're actually going to see that when we compile this and we create the WASM file, the name of the WASM file is actually going to be this. So we're going to have to make reference to it in the future. Authors. So that's going to be used when publishing the crate. So I just want to give a shout out to the Near web series that we're involved in. Version, that's the crate versioning number. Edition is the Rust edition that we're going to make reference. Lib is like, that's sort of like the target library settings. I'm honestly not an expert on that, but it should be fairly standard across any sort of Rust development you want to do in relation to smart contracts. Some of the things you'll see here, which might have more to do with like configuration aspects to it. It's like, I'll kind of get to it in the end. I'll put up a repository with like, with a lot of example code, and you can sort of like, you'll be able to sort of like copy and paste sort of like templates from there. And then as your development goes along, you sort of maybe need to make changes to them and get a little deeper into it. But at the beginning stages, you should sort of be fine with what's there in existing projects. Sort of like if you've seen in the package.json in doing sort of like Solidity development, you have a dependencies area. So for this, definitely would be using the Near SDK. I know that was brought up in session 4, so thanks for those guys for sort of touching on that a bit. I just want to post a quick link here on the Near SDK. So there's some information there, and something we're going to get to in a little bit later, which also I think Ryan touched on a bit. Oops, just some stuff on the Near token, Near contract standards there. That will definitely help you a lot from the standpoint of contract development. Okay, and then here, profile.release. There's some arguments in here that I'm not entirely familiar with, but one of them that I definitely understand is this setting this overflow checks to true. If we didn't set that, it's not going to be an issue for this particular project because we're not going to be, well, it's a counterexample. We're not going to be counting up to the point where we'd have an overflow condition. But if you have this, you're not going to have those overflows happen silently. There's going to be basically the smart contract and sort of stop function, which is probably more what you want to have from a security standpoint, as opposed to having these overflows. If you take a look online, you'll find that there's been potential to sort of exploit contracts using overflow and underflow attacks. Okay, so now let's actually get into writing some of the code for our contracts. I'm just going to go into the library.rs file, and we're going to import some of the stuff we want to use. So we need Borscht to serialize and deserialize to write and read from WebAssembly. We need env for general Near stuff, and we need Near bygen. So env is from the Near SDK, and it gives us access to a lot of important functions in the env module. For this particular example, I think all we're really going to be using from it is a log function, but there'll be lots of other stuff that you pull in there for more sort of advanced projects. We also need the Near bygen macro. That will ensure that the code is generated such that you can create like a valid Near contract. Yeah, so it will ensure that like through the compilation process, that code is generated such that it can be a valid Near contract, and it will help expose the intended function to be called externally. So here's a few links on that Near bygen, and here's some stuff on the env module. And then I'll get a little bit to later on in the project. Okay, so in terms of importing resources for the current project, this sort of use notation, it basically creates a shorthand so that we can access these specific imports from the modules using shorthand. So we can just basically call on Borscht deserialize directly or env directly, as opposed to otherwise we'd have to sort of write it out like when we want to access something from there, we can write it out like this. So it's sort of there from like a code cleanliness standpoint. Another way to import things is to use what's called a module, the keyword module, and that works a little bit differently, but it's kind of similar. I don't actually think we're going to be using it through this project, so I'm not going to get too much into it. But as we saw in the last demo, so we try to start with like setting up our Rust contracts by defining a struct. So this is the core struct of the class that we're going to make. So let's see, we're going to call it counter. It contains a single field, a variable called val that is an 8-bit integer. So yeah, it'd be cool if someone in the chat could sort of say what the largest value of an 8-bit signed integer can be, what the lowest value can be, and also what the highest value of an 8-bit unsigned integer could be. Yeah, so just see some engagement in the chat would be cool. So I'll let Ryan and, oh, Brian's gone, so maybe I'll let Dorian sort of like validate those answers. So getting back to the macros, that's these parts here. There are a few different kinds of macros in Rust. So I'm just going to talk about the derived macro here. So a really simple way to think about derived macros is that sort of expands on what was touched on in the last section, is that like, let's say we wanted to have like a derived macro, we could define this somewhere, like we basically like derive this macro somewhere else, similar to how we define a function. We'll get to that in a second. And we could define a function that's like, say, let's just say like hello world. By putting like this derive and then like Borscht deserialize, or in the example I just gave, hello world, we'd basically be able to, this thing that we're creating here would be able to actually have access to that function, for example. So it's sort of like, it's not quite like inheritance in sort of like the traditional classic object-oriented sense, because you couldn't like cast from let's say this type counter to like the counter that you're deriving from, but you would have access to its sort of implementation. So it's kind of similar in that sense. Okay, so yeah, now let's get to the implementation. So we're just going to start. Do this a little messy because I'm going to leave it on. I'm going to leave this sort of bracket open when we move. And one thing which hopefully Dorian can comment on in the chat below is we have to use the near bindgen here, sort of for the similar reasons I described before, but we don't actually need to use the Borscht deserialize and serialize here. I'm not entirely sure why that is. Like I could sort of speculate on it a bit, and maybe we'll have a convo about that at the end. But sort of getting back to like my initial point is that, you know, from like the learning standpoint and being able to get contracts out there and test them, like I wouldn't worry too much about that. That's sort of like for basic stuff, that's sort of like the standard sort of like a pattern to follow. So just probably stick with that right now and not worry too much about it. But yeah, getting into the function here, we're calling it get number. It's going to be a public. So public methods can be viewed by anyone, and it's going to have a return type of assigned integer I8. Yeah, so that's that. Now let's define the first function that we're going to be doing. Sorry, the second function. This is going to be called increment. We're going to do increment, decrement, and reset. And then we are going to add one internal function, and then we're going to add some test cases. We're going to run the test cases, and then we're going to do a dev deploy. And assuming I don't do anything wrong, deploy to test that as well. So just kind of looking at the increment function, we have this, this is sort of an important part here, this and mute. So all the functions which alter state, so like set functions, anything that's going to interact with anything that's stored in the contract or add something to the blockchain is going to have this and mute, whereas view functions here are just going to have the and self. That's, I believe, sort of inherits from like sort of like the Rust development standard, how they do things in there. Here, sort of like for the non-developer background people. So we're kind of using this dot notation, calling on self, access a field or a variable that's within self, and then we're going to increment that value by 1. So like one other way to write this could be like self equals self.val plus 1, but in programming you end up adding and subtracting ones a lot, or just sort of incrementing existing values by sort of like set amounts, and this is sort of like a shorthand to do that. Okay, so here, one of the things we also do in Rust is we have like, if we want to define a variable that's just sort of like set within the scope of something, we use this let. So we're going to say let log message equals format. So this is just the string, and this being, I believe, just a call from the Rust library and reference to the self.val. And then we actually want to log that message to our environment. And so we're going to be actually calling log message. So maybe one way to have made that cleaner, which would have been to within here do : env and then : log. We could have pulled that in directly without making env log here. But yeah, so okay, and then here at the end we also make a call to an internal function here, which we will define at the end. Okay, so that sort of sums up like sort of like the rough pattern for defining functions there, at least to the extent that we're going to be doing in this project. So there's the decrement function, similar. Instead of adding one, we're going to be subtracting one. And a reset, which is basically going to set the value of the counter back to 0. And as I said here, let's just close that off. Okay. Yep, it's okay. Now let's add that internal non-struct function I was talking about. So this is sort of internal calls only. So this is something that not the whole world can see. So it's like, you get tired of your mom calling you, you give her a public function, you want an internal function, people in the crew. And that's kind of how it works. Yes. So now hopefully Dorian can comment on this a little bit, but this is like, this function does not have to derive from near bindgen. Or rather, yeah, it doesn't have to, I think it's derived from near bindgen. It doesn't have to call the near bindgen macro, and it doesn't have to derive from board serialize to serialize. And I think I sort of understand it from the bindgen standpoint, because it's not going to be exposed to anyone calling from the CLI, for example. It's just going to be called from within the contract itself. So I don't think it needs to go through that bindgen macro. But why it doesn't actually need to go through serialize to serialize? I guess that sort of falls into the similar rationale. You're not, it's not communicating from the blockchain to outside of that. It's all sort of happening on chain. So I think that's why it doesn't need those. Okay, so let's find some tests. Tests are they're all gonna start with this macro CSG test. That's just gonna let the just let Russ know that it's a test. Let's get a little bit into some of the things that we're importing there. So mock blockchain is basically a mock blockchain for testing, and testing environment and VM context we'll get to in a second. Yeah, so let's write a function that is going to help with our tests, and that's going to set the context in the VM that we're going to use to running our tests. So this is a fairly big block here. Get into it a little bit in a second. Okay, that's looking okay. Sorry, Katya, I just saw that message. Thanks. So I haven't played around with a ton of these yet. I've sort of been importing them from existing projects and using them as standard, but I'll walk through it a little bit. But to give some example, like if you were doing development in hard hat on like Ethereum, you'd be able to sort of like fork mainnet and testnet for specific block testing. I'm not exactly sure if you can do the same here. I think for this example, that's not going to be happening, but that would be something cool if Dorian could comment on that a bit. Yeah.
Sorry, what was the thing going to be coming on?
Yeah, it was just so like I've done like development in hard hat, and it's like you can sort of like set up the hard hat config to basically fork a copy of the mainnet or the testnet that you want to do your development on. So that could like allow you to like communicate with like contracts that had been deployed or were existing at that specific block time. And I'm just wondering if you can use sort of VM context for something similar for testing your smart contracts as well.
I mean, in terms of like testing our smart contracts, like we do have like some like a variety of like test suites you can play with. Like we have Workspaces RS and Workspaces JS as our like primary tools for testing. So they kind of like port over like they allow you to essentially create like a node from on your local machine, and you can like pull information directly from the chain.
Okay, great. Yeah, thanks. That helps a lot. I don't know if you have a link for any documentation on that. That'd be great if you could post it in the chat.
Yeah.
Okay, thank you. Okay, so I'm just gonna walk through this test a little bit. Again, starting with a macro, just to sort of let everything know that it's a test. We're just gonna test the increment function. So test environment will initialize the blockchain interface with the VM context, which was returned through context, get context here. Vec passes back here will pass an empty vector. We could have passed it as an argument to the VM context fields. So basically passing something to create this. But we sort of set all of those. It's sort of hard to find those in the get context function. So I don't think you actually have to worry about that. We're going to let a mutable type contract here equal to the counter, and that's been initialized with a value of 0. Then we're going to call the function increment on that contract, and we are going to print the results of that call to increment using the get num method that was defined in the contract, the counter contract that we set earlier. And then we are going to call assert to ensure that the result of that get num is equal to 1. So this is like a test for increment, but it really also sort of tests the function of the get num method that we set up as well. So we're going to follow that for testing the 2 other functions that aren't being tested yet, because get num is being tested. So we also need to test for decrement, and we need to test for reset. So let's just bring in tests for those. And it looks like our tests are closed off there with a curly. Okay, I think now we can actually test the code. So that's kind of exciting. Let's hope I did that all right. I'm definitely kind of nervous. But yeah, one of the ways to do that is to call cargo test, and then no capture. And let's see how that goes. Okay, well, it started without any major errors. So compiling, building. And this should actually run the test for us as well. We would see a log at the end of that. So yeah, this is up until now pretty much how you would go about writing a simple smart contract, writing some tests on it, and then actually running those tests. You can see that it's all sort of done within one single project folder. And yeah, I mean, it's all done in Rust, and it's all sort of integrated into one place, which is nice. Whereas like if you've done dev work in Solidity, like you can use sort of different tools to help with that, like Hard Hat or Foundry and things like that. But yeah, here we sort of see, we see the results of our tests. It looks like everything passed okay. So like we have you can see like the results of the print lines were called here, and they're printed to console. And then we can see that when like these things were initiated, or rather when they were built, this test macro, it actually sort of like, and then this assert, when that was passed, like, yeah, so the test passed okay. So that's great. Okay, now let's actually take a look at what was built. Okay, here's the debug. Okay, now let's compile and build a smart contract so we can deploy it. That is going to be this command here. Okay, boom, we saw our WASM folder, and we should see our WASM file created in a second.
Oh yeah, I don't know if you saw what I put in the chat about the WASM 32 unknown. Just simply just mean the unknown knows just means like you're compiling on almost any machine and running on almost any machine. Yeah, sorry, I don't know if you saw my message earlier.
No, I didn't. Thank you so much for that. That makes a lot of sense though.
Yeah.
Okay, so it looks like it went through okay. We go to release, we can see our WASM here. I know there's a way to actually do that building such that it will print out sort of like a human readable version of that, but I don't have that on hand, and I'm just gonna keep it going. So let's deploy this to testnet. I'm just gonna minimize the chat. So oops. Okay, can you guys still see my VS Code? Okay, great, thank you. I think I'm in the right directory. Let's see. Lots. Okay, what's the directory? Okay. Okay, you guys can't see it, but I just opened up another window for me, just like when you guys would have set up your wallet. It's asking me to log in. I'm going to log in. Okay, so now let's deploy to testnet. This part I have sort of intentionally set up so that it might go wrong. Because I want to explore some of these sort of 8, I forget the term that Ryan used to describe them, but sort of 8 composable transactions that we use on Mir. So I'm trying to deploy it to like my master account. We can see that I've already got some stuff there. So I'm actually not going to deploy it there. I'm going to create a new account. So this is one of the, so that first CLI command I called deploy, that's one of the 8 composable interactions. Another one would be create account. So I'm going to create account testing 4. Okay, that created that account. I created it with initial balance 10, and I called that from the master account here. So now let's see if we can deploy to that testing.4. 2 things might go wrong here. One, it could be that the credentials were created in the WSL and they need to be moved over to sort of my Windows. The other could be that it has insufficient balance. So let's see which one. Here that might have the balance we want, so we can sort of transfer some funds from an existing one. Testing 3. Okay, this guy's got 40 near, so I'm going to show an example of deleting an account. I could transfer from testing 3 to testing 4, but I just want to show calling delete. So near delete testing 3, omori.testnet. Delete that account. This account here at the end, omori.testnet, that's going to be the beneficiary of that delete. So he should get that 39 point something near. Let's send 30 near from omori.testnet to omori testing 4 omori. Okay. That is looking good. Just quickly. Oops, sorry guys. So near deploy, yes, deploying to testing 4. Hopefully this goes through. Otherwise, yeah, not good. Okay, it looked like it went through. That's great. Now what I want to do is I want to call some of the functions that we'd find. So this is going to be where the contract was deployed. Now we're going to call it from omori testnet. We're going to call the increment method. So schedule a call, testing 4, omori.testnet method. Okay, increase number to 1. And one thing to note is these logs that are displayed here. Those are, if you remember, the logs from the env module that we called. There you see it right there in the command line posted. One of the things that we're going to see later is when we look at a fungible token example. There's actually ways to sort of display what are called transaction receipts and have those actually show up on the blockchain. And that's something that's super important. For, let's say, anybody wanting to do some sort of on-chain analysis, and maybe at the end of it, if you guys got any questions about doing on-chain analysis, I've been doing some work with the graph to do on-chain analysis for NFTs and DAOs. So there's sort of some cool stuff there. So let's call decrement. Let's call. Okay, so now you see that it's decreased to 0. Let's call increment again. We should get back up to 1. And then, okay, back up to 1. And then let's call reset. Oh, I think there's just a small error in the syntax there. There's no space between reset.
Yeah, I think there's like I don't know if like anyone has any questions or okay, the Alice in testing was unclear. Alice in testing, like for the test suite, or like I'm a little confused by that statement.
Hi, thanks, Dorian. There was a line of code which I think created a fake account in order to run a test on it. I'm not too sure. It said something about creating an Alice account.
Oh yeah. Let's see. Oliver, which repo did you pull this from again?
Actually, I posted the link in the chat. It's basically the Rust counterexample that's in the near docs section. So I didn't pull it from a repo. I just built it from scratch there, following the commands there. But essentially what it's doing is it's just setting like some accounts that you'd make reference to within the testing environment, but then it's not actually making reference to them in the tests.
I've seen the Alice used in like other contexts too. Yeah, it's just making a pseudo account for testing purposes. Let's see.
Like when I do a test, do I have to make this Alice account if I'm not using it?
I mean, I would suggest just copying the template there.
Yeah, that's why, because I mean, I've copied it, but I just wondered for myself as to why it's there or what do I do with it. So yeah, I mean, if you're not too sure, that's fine. I was just wondering.
Yeah, I'm trying to find like an example of like, because I know I've seen like Alice, and I think there's another name that we always kind of use. Kind of just use, but it's just like it's just like simulate. I think so. Essentially, like near workspaces, what you can do is like you can like simulate creating an account and like deploy an account to like your own quote unquote node on your local machine. So like I think I found like a kind of a neat example. It's like a very small one, but like so like with these kind of like fake accounts that you can they can create using near workspaces, because I think some of our tests are like written in your like using or created using your workspaces. Like you can do things like test the transfer of an NFT between two accounts. You can have like Alice or Bob as like your accounts that are created on your machine. Make function calls, like attach gas. Like here, I'll put like a little link for.
So is it like an environment that we set up in Python, for example, where you're isolated from the base distribution? Is it like you're isolating away and you can do some stuff like test-wise in that space? Is that what you mean?
Yeah, exactly. Like, so like what's cool about network spaces is like when I say it creates a node on your machine, like you can do like essentially like you can almost think of it like creating your own like little mini test version of your blockchain, and like, but in this case, you can do things like control the environment of it, meaning like you can set like you can set the number of like you can fix the number of like block height you're at. You can like I think you can control like event logs like more reliably. So if you have like some sort of like time-based like code, you can like deploy it better. Or you can do like just like simple things, just like normal like contract development and like just testing, but like on your local machine, like making normal function calls, running smart contracts, deploying it onto like your pseudo accounts in a way. Yeah.
Yeah, thank you for that. Thanks a lot.
Okay, great. Thank you so much. So yeah, we'll go through like a simple FT example, maybe talk about a few things in here that we didn't see in the last one. So we're going to do a dev deploy, but before we get into that, I want to talk about this thing here. This is a pretty important macro that you're going to come across. It's called the init, and this is going to come to when you want to, we're going to do a dev deploy, and then we're going to sort of initialize this contract, sort of like calling the constructor that Ryan was pointing to in the context of Ethereum development. And this sort of hash net is going to tell the compiler that this is going to be like the constructor. I think actually in this one, there's two. One, we can construct it with new default metadata. The default metadata is here. And then the second one would just be, we're going to actually pass in some arguments. We're also going to hopefully touch on a few other things in here. So Near sort of has like 4 like critical development features for working with smart contracts. And you would have seen them if you've done stuff in Solidity. So that's like assert, storage, persistent collections, and context. So persistent collections, you saw a bit of that in the last demo from Purdue. And that was basically when they were sort of like creating those collections on the blockchain, and they had to do that with sort of like a unique string to sort of like make them like uniquely accessible. So that's one of them. Another one is assert. So we saw sort of assert in the context of the test, but that's a little different. So assert is like an important thing for smart contract development, because like good smart contract development sort of like operates on this principle of like check, effects, and then interactions. And like sort of like one of the main reasons, that's like one of the big drivers behind that design philosophy were things sort of like reentrancy attacks. So basically what was happening is that contracts would be like basically like you might call them to like, you know, return, let's say, some sort of reward from the contract from you. And if it sent out that reward before it changed its internal balance, what someone could do is they could create what's called a reentrancy attack. And what happens is that like when that contract that called to get the balance from it, when it receives funds, what happens is that reception of funds would trigger what's called the fallback function. And you could program that fallback function to immediately call back to that function to receive funds again. And that's basically where the control would be. So the code actually wouldn't pass to the next line where it would update the balance to tell the code to say that, no, this guy's already got his money. It would just keep on draining all the funds in the account. And so like one of the critical things you want to do is sort of like check, assert, check all the things coming into the contract are consistent with what you're expecting, do the effects. So basically like change the internal balances. And then from there, do interactions with other contracts, like in the example I gave, like deposit the fund, for example. So assert is like sort of like an important part of being able to achieve that safe design paradigm within smart contract development. Yeah, so I wanted to touch on that. Context is another one. Context is important because that's basically like pulling like information from like the transaction. So like, you know, if you're calling a function on Ethereum, like it would be an example of context would be like message sender, like what's the address of the message sender, or what's like the near deposited with that. So I'm not actually going to go in and show where context is called on in the code here, but you'll see that when we call on some of the methods associated with this contract, there will be some sort of amounts tied to them. So this example would touch on using context. So I've already built this. If we did want to build this quickly, this project, I can actually post a repo at the end of this, but we would just do something like build sh. This is basically just like a bash command that would call the build file here, sort of similar to, sorry, that's a mistake. Sorry, sort of similar to the command we saw when we deployed the counter example, but we're going to do a dev deploy. And so when you do a dev deploy, what it's going to do, it's going to create these sort of, Cargo is going to create these dev accounts for you, and it's going to actually deploy the contract to these accounts. But I've already ran this and deployed it to these accounts. So I'm actually going to delete them. And then I will run the dev deploy. Yes, okay, that got deleted. Now let's do a dev deploy here. And hopefully this goes through properly. Oh, let's try running it from dev. Okay, yeah, let's see if it's working. Yeah, so done deploying here. We can see that it created the dev account and the dev account environment. Let's just make sure set a environment variable, contract name to that dev account, so that when we do the deploy in the next section, it's gonna be that. Okay, there's the dev. Okay, now let's call that an initialization function that we saw in the smart contract, and give it some fields. So let's call it the near web series token. We'll give it the symbol, NWS TKN. We're going to, we're going to call it from the dev. We're going to give it, call it from that account here. Okay, so we see that it was successfully deployed. So that's great. Now let's actually put this on testnet. So we're going to call near login again from this terminal. It's going to open up another window for me. If you wanted to do this actually to mainnet, you would say before near login, you'd say near environment, and you'd set that equal to mainnet. Yeah, and it would open the window and give you an option to log in with your mainnet account. Okay. Now let's create an account for which we can deploy this contract to. I'm going to call it nwsft.omurray.testnet. So the best convention here for sort of like deploying contracts within Near would be to actually go to the Near wallet, create an account with the name of the contract that you want to deploy your contract to. So if we just wanted to call it to like Near web series ft.testnet, we could go in there, create that account, and then we'd basically we'd have to go through some process of like ensure that we have the keys generated and the keys allocated in the right folder, such that when we ran these commands through the near CLI, it would access them. But that stuff is, once we're done, I'll just remind me and I'll try and pull up the guides on how to do that properly. So again, let's set a local variable. In this case, okay, yeah, we set ID equal to the name of the account that we wanted. And now let's try and deploy it. This should be similar to the command that we ran with the counter example. Yeah, that's the name of the WASM file. Okay, it's in the res folder. This should go through. Also, the account was created with initial balance of 30, so we're not going to have to go through that funding process we went through last time. It looks like it went through. I will just post this. Well, I don't know. Where's my chat? Where's my chat? So near view ID FT metadata. Ooh, that's not good. I'm not sure why that happened. Let's see. Can I call anything else? We want to do this operation here so that we will be able to transfer funds to it. And then let's call it transfer. Interesting. I'm not sure why that timed out. Looks like that went through. Let's call it transfer over 19. Okay, looks like it went through. Let's see the balance is there. Yes. Okay. So that sort of concludes the live demo portion. I hope you guys got something out of that. I know I did. It's a super pleasure. But like I sort of said, like this is sort of pulled from and making reference to a wealth of examples that are available from near. That's a great one. I think there's like 83 examples within there. A great place to do further work is here. This is something I've learned a lot from the live contract review, and also here the live app review. Katja is asking a question.